All right, so here we see what we've been, or a definition that states what we've been saying, which is the instantaneous range, or excuse me, the instantaneous rate of change of a function f of x at a value a is the derivative f primed at a, right? So f primed at a is the same as saying the instantaneous rate of change of this function at the given value a, okay? All right, so basically we can just use our same formulas and same procedures, methods to evaluate instantaneous rate of change as we did to evaluate the slope of the tangent line and the derivative at a point. All right, so here we have our rate of change of temperature. So a home owner sets a thermostat to so that the temperature in the house begins to drop from 70 degrees at 9 p.m., reaches a low of 60 degrees during the night, and rises back to 70 degrees at 7 a.m. the next morning. Suppose that the temperature in the house is given by this formula here, for where T is between 0 and 10, and that's the number of hours past 9 p.m. Okay, so T is the number of hours past 9 p.m. So find the instantaneous range of the temperature at midnight. Okay, so at midnight. So at midnight, what would T be? So if it's T is the number of hours past 9 p.m., how many hours past 9 p.m. is midnight? Well, midnight's at 12, right? And so if we do 12 minus 9, that's 3. So 3 hours past midnight, right? So T equals 3. So basically what we want to find here, and we have capital T of little t, but we want to find capital T of 3, right? We want to find the derivative of capital T at 3, and that'll tell us the instantaneous rate of change, right, of the temperature. So when you see instantaneous rate of change, think of the derivative, and so we're going to calculate that. So our formula here for that will be the limit, and I'm going to use the our increment formula, so with h in it. So it'll be T of a, which is 0 in this case, plus h, right, minus T of 0 all over h, right? And so the nice thing about 0 here is 0 plus h is just h, right? So this just turns into T of h. All right, so I just have to find T of h and T of 0, which both are pretty straightforward. So T of h is just going to be, if I put h in for all these t's, right? So it's just going to be 0.4 h squared minus 4 times h plus 70, right? So I just replace the h's with t's. There's not really anything I can do to simplify. So I just leave it like that. Then T of 0 is if I replace all these t's with 0, right? And what's going to happen is this will turn into 0, this will turn into 0, so all I'll have left is this a constant, right? That's what happens when you plug in 0 to these polynomials, you just get the constant. So T of 0 is going to be 70. All right, so I'll have put a 70 in that spot. All right, and so what I'll end up with is the limit as h approaches 0 of T of h, which is this. So 0.4 h squared minus 4h plus 70 minus T of 0, which is 70, all over h. Okay, and so as we can see, what happens, and what's happened a lot before, is those 70s cancel out, and so now we end up with that expression, which we can factor out in h, right? So we can factor out an h from there, so we end up with h times the quantity of 0.4 h minus 4 all over h. Okay, and so now that these match up on top and bottom, they can cancel out, and what we're left with is the limit as h approaches 0 of 0.4 h minus 4. And at this point, we can directly evaluate because we don't have the threat of a 0 in the denominator anymore. So it's just going to be 0.4 times 0 minus 4. And 0.4 times 0 is 0. So 0 minus 4 is negative 4. All right. So that's the value for t primed at 3, or in other words, the instantaneous velocity at t equals 3, right? All right. So that's how we do that. So very similar to what we've been doing, just a lot more practice of the same thing. But once again, now we have a little different context. Instead of just talking about the derivative in an abstract sense, or the slope of the tangent line graphically, now we're talking about actually real life situations, or models of real life situations where we have a little more context involved, right? And we're finding instantaneous rate of change or instantaneous velocity.